Let's do a second derivative example. That's a little bit funny to say. Second derivatives are something different. I'm talking about a first derivative, but it's a second example. We did x squared last time. Let's do square root of x this time. So my function now is the square root of x. I'd like to find the derivative of this function at some number in the domain of this function. The domain of this is all x greater than or equal to 0 for our class because we're not allowing imaginary numbers in our class. Square roots of negative numbers are called imaginary numbers. That doesn't mean they don't exist. They do exist. It's just a label. People at first thought they didn't exist, but they do. They are honest to goodness numbers. It's kind of a fun label. But for us, the domain is the interval from 0 to infinity, like that. In set builder notation, it would be the set of all x such that x is greater than or equal to 0, which is equivalent to saying 0 is less than or equal to x. Anyway, the graph of the square root function looks about like this. It's really half of a sideways parabola. And we're interested in knowing the derivative somewhere, let's say at 4. I'm interested, like I told you last time, in knowing a slope of a tangent line. If x is 4, the square root of 4 is 2, y would be 2. I could draw a tangent line at that point, which is the line that best approximates the curve at that point. And I could ask, what is its slope? That's what the derivative is meant to represent. It's defined in such a way that it gives you that slope. It really is the definition of the slope of the tangent line. It's always this kind of limit. The limit as h goes to 0 of f of 4 plus h minus f of 4 divided by h. The fact that I'm using a 4 there means I need 4s here and here. What's h? It's just another letter. Why h? It's just traditional. Sometimes people use a delta x instead of an h to emphasize it is a change in x. And that's fine as well. It's tradition, okay? H doesn't really represent anything. We just need another letter. I mean, as far as why we use the letter H. In this picture, H does represent something. It represents a distance between 4 and a number to its right if H is positive. It would be a number to its left if H is negative. And we do allow H to be negative. This is technically a two-sided limit, though I'm not drawing it that way. And what are we doing? This thing is called a difference quotient. Difference quotient. It represents the slope of a secant line. A secant line on a circle just connects 2 points of a circle, 2 distinct points of a circle. A secant line for a curve connects 2 different points on the curve. There's 2 different points I'm trying to draw there. One right here, one right there. That secant line is not the tangent line, but it's close if h is small. As h goes to 0, the secant line becomes more and more like the tangent line. You might say in the limit, the secant line does become the tangent line, though that phrasing is a little problematic. What does it mean for one curve to become another? Well, that's hand wavy. This limit, if it exists, is the definition of the slope of the tangent line. By definition, nothing to prove. But you do have to prove the limit exists by, in this case, calculating it. What's the function? It's the square root function. I have to use that function. Oh, and lo and behold, I've got a square root problem with square roots in the numerator. How about that? There was a reason I did the first example today. Square root of 4 is 2. That's nice. But I can't get rid of that square root of 4 plus h so easily unless I rationalize the numerator. Plus sign. If I do it to the top, I've got to do it to the bottom so that I'm multiplying by a big 1 and not changing the expression when it's defined. I FOIL out the top and magic happens. Square root of 4 plus h times itself is just 4 plus h. Because I have a minus sign there and a plus sign there, the outside and inside products cancel. It's a 2 times square root of 4 plus h and a minus 2 times square root of 4 plus h. They cancel. Then last times last is negative 2 times plus 2 is negative 4. The 4 and the minus 4 will cancel. On the bottom, I still have a square root, but once again, that turns out to not be a big deal. I divide out the h's. Divide those out. Remember, realize, 4 minus 4 is 0. H divided by h is 1. So it's not like it's becoming a 0. And so I try to avoid saying the word cancellation there. I say divide out. I'm not getting a 0 on top. It's a 1. And what's left down here is a continuous function of h when h is close to 0. It's continuous at h equals 0. I'm not dividing by 0. I can plug in 0. The answer is 1/4. That is f prime of 4. Can I justify each equality? That equation is just the definition of the derivative. Def of deriv. This equation here is substitution. I'm using the function formula. This equation right here, we can just say is algebra. I'm multiplying by a disguised form of 1, so I don't change the expression. There's more algebra right there. This equation is more significant, more than just algebra. You could say it's algebra along with the fact that, technically speaking, the value of the limit is independent of what happens to these functions at h equals 0. That's kind of a long-winded thing to say. I'll allow you to say definition of limit for short. But it's really the fact that I had, in that definition, I had the 0 is less than the absolute value of x minus c. I allowed x to not equal c. Yeah, this function is not defined at h equals 0. It's happening. There's a removable discontinuity for this function at h equals 0 as a function of h. Have I graphed this function of h? No, I haven't. I graphed the original function, the square root of x. I have not graphed this function. I'm just doing algebra. This technically is also more significant. That's continuity. I'm not dividing by 0 when I plug in h equals 0 here. This function is a domain where h is greater than or equal to negative 4, and for all those values of h is continuous. No problem with dividing by 0. And that's just arithmetic. Right? Just whatever. 4th, 5th, 6th, 7th grade math, arithmetic. So 1/4 is the slope of the tangent line. What's the equation of the tangent line? Well, I can use the fact that I know it's got to go through the point 4,2. So I can use point slope form. The equation of the tangent using point slope form would be that, right? The slope is 1/4 and it goes to the point 4,2. Solve for y as a function of x. Get y is 1/4 x plus 1 is the equation, simplified slope-intercept form of the equation of the tangent line. Let's end class by confirming it with our technology here. So I'm going to graph the square root of x. I'm going to graph 0.25x plus 1. They are different functions with different graphs. I'll go from 0 to 8 to start off with. 0 to 4, say. Here's the square root. Then the tangent line at 4 looks pretty good. Let's zoom in to see if these two curves look more and more alike as I get near 4. So now I'll go from 3 to 5. And maybe 1 to 2. Oops, that was a bad window. Oh, 1 to 3. There's the square root. Here comes the tangent line. You can barely tell the difference between them. And as you zoom in closer and closer, you definitely cannot tell the difference between them. They are different, but they look more and more alike as you zoom in closer and closer. Have a good day.